we turn to describe a demo of the IRLS as a way to get the basis pursuit solution. Here are the details of the problem we are about to solve. This is the penalty function we will be minimizing. A is a 100 by 200 matrix of random entries and normalized columns. We create B by first creating a sparse vector x star. This vector is of length 200 and it has 4 non-zeros in random locations and values away from 0. The vector B is created as A times x star plus a zero mean wide Gaussian noise with sigma equals 0.1. Our goal is to minimize this problem and get a solution that is as close as possible to x star. We run the IRLS for this problem, and the first thing to notice is that we should run it for varying values of lambda, since it is unclear what is the best value for our needs. The continuous line graph presents the distance between the obtained solution and x star as a function of lambda. As you can see, for a value of lambda around 0.1, we get the best performance where x star and the estimated x hat are very close. How could we tell that this is the best lambda value if we have no access to x star? The answer is based on the energy of the residual, ax minus b. When x star is plugged into this residual, the error is exactly the added noise, and its L2 norm squared is given by n times sigma squared. This would serve as our epsilon squared. In the dashed line, we show the ratio between the actual residual L2 norm and this ideal epsilon value. We show the absolute of the log of this ratio. When this ratio is 1, the log gives a 0 value. When the residual energy is lower or higher than the epsilon squared, we get a value above 0. Thus, the minimum of the dashed curve points to the lambda that satisfies the constraint that ax is epsilon away from b. As you can see, there is a lovely agreement between the two in detecting the lambda to use for getting a solution closest to x star. We present here 3 different IRLS solutions obtained for different values of lambda. The middle one represents the best lambda, being nearly 0.1, and as can be seen, the 4 true non-zeros marked in red are detected very well. If lambda is substantially smaller, the solution tends to be denser, with many non-zeros. In the other direction, when the lambda is too high, the solution is sparser and the non-zeros are heavily penalized, thus being very small. The last graph we show presents the Lagrangian penalty expression as a function of the iterations. While we see a descent in the first 4 iterations, we do observe a slight ascent later on. This comes back to something we have mentioned before. We have no guarantee that the IRLS is getting to the optimal solution, nor that it leads to a consistent descent in this penalty.